All right, so today we are going to continue our discussion on memory hierarchy, and we are going to talk about the causes and remedies to cache misses. And I name it the hardware because we are going to talk about how to use hardware optimization for memory hierarchy performance. But before we start, it's always important that we put everybody on the same page. And the most important thing, today I intentionally skipped the slide on volumetric architecture because I know you guys have been hearing about it for weeks. But the thing is that, okay, in volumetric architecture, processor and memories, they are so important. However, there is a huge performance gap between processor and the latency of accessing memory. So it turns out that the most important topic for now for computer architecture at this point, before we're talking about the memory hierarchy optimization, it's actually how to optimize the memory performance. So turns out that our solution is that we build memory hierarchy by adding a few small SRAM-based caches. And the reason why the SRAM caches will work well is because your code has locality. And with that hierarchy, so what happens when we access cache is performing memory access from your processor is pretty much like this. So for example, your processor may issue a move command that would intend to update data in your memory. However, as we said, this is a strict hierarchical structure. So it turns out that your processor always interact with only one unit in the memory. That is actually the topmost of the memory hierarchy. That's your L1 cache. So the processor itself won't talk to anyone else except for the L1 cache. And then the processor will consult if I have the data right there. And if the data is presented in the L1 cache, then we consider this as a hit. And if it's a read, then the cache would directly return the data to the processor, depending on how many bits of data, how many bytes of data that the instruction is requesting. And if it's a write, then the L1 cache will receive the data, perform the update of the corresponding bytes within its own storage. In a way, how the cache knows if it's a hit or a miss is based on partitioning the memory addresses that your instruction is requesting. And how we partition that is based on the C equal to ABS that we talk about in the class. And but the most important thing here is that for each memory request, we partition the memory address into tag, index, and offset. We use the offset to figure out which byte or starting from which byte of data within a block that your data might be located. And we use the index to figure out which set of blocks will contain the data you want if it's in the cache. And then we use the tag to finally figuring out if it's something you are looking for. And okay, if it's a hit, if it's a read, we return it. If it's a write, we perform update and we set 30-bit. And the reason we want to set 30-bit is because we want to know if this is the if we want to know that block is the most up-to-date content. And then after, and however, if it's a miss, then what happened is we would have to look for it from the lower level memory hierarchy. And however, most of the time, even though I found it from the lower level memory hierarchy, I still need to accommodate it in my local storage, as I said, because your processor only interact with L1. So everything has to be present in L1 for the processor to continue. And so sometimes I have to kick out some stuff. And the way how I kick out some stuff is that for the set that the data should be locating, I pick the one that is least recently used. So so for example, right, like if you have a roommate, right, and if you want to kick out someone, you probably would pick the one who is typically not at home, right? That's the policy. Although most of the time I would rather keep the one who is mostly not at home so that I can enjoy the whole house. But that's another story. But the thing is, okay, at this point, I may kick out something. And as I said, if the block itself is dirty, if I kick it out, then no one would obtain that up-to-date copy. So what I end up doing is I have to write back the block first. And then after I written back the data, I can finally fetch the block that I wanted, because at this point, I got the data I want to be in L2. However, there is also a chance that, okay, the block that I want is not even in L2. So then you have to repeat the same process again by fetching it from the lower level memory hierarchy. And again, you have to accommodate a new block. And there is a high possibility that the data has been written, so you have to write it back. So once we accommodate all above, then we can gradually return the block to the upper layer of the memory hierarchy and finally perform the update, the operation that you want. And again, how to partition this memory address, you can use C equal to ABS, and C is the capacity, A is the weight associativity, B is the block size, or say the cache line size, and S is the number of sets. And if you have a direct map cache, the A should be set to 1. If you are having a fully associativity cache, means that your cache block can go anywhere in the cache, then you should set 1 as the number of sets. And the number of bits in the block offset would be log B, and the number of bits in the set index would be log S. So that's the usage of C equal to ABS. And use C equal to ABS, we are able to simulate a two-way cache, as the last time we talked about. And we also try to simulate the performance of your code on an NVIDIA processor like this. And we know, well, 100% of them are misses. We also have been simulating this on an Intel Core i7. And we know with higher weight associativity, the same pieces of code performs better on Intel processor. So now, today we are going to continue our discussion. And today we are going to talk about how to optimize the causes of cache misses and how to optimize them. And but before, if you want to talk about the remedy of something, it's very important that you figure out what are the root causes of something. So that's why we start with the taxonomy and the reasons of cache misses, so that we can address the problem of cache misses accordingly. Okay, so there are 3 C's of cache misses in computer architecture. So the first one is called compulsory miss. The first one is called compulsory miss. Hi. By any chance, you know what is instruction level parallelism? No. That's a compulsory miss. Is this the first time in your life you heard about it? Yeah, that's compulsory miss. Now you understand. Compulsory miss means cold start miss. So if this is something your code never reference, That's compulsory miss. And the second type of miss is capacity miss. So capacity means that, okay, the amount of data or the amount of instructions that the program needs to access within a period of time, within a window, it's just too much for the cache to accommodate. What does that mean? Is that, okay, no matter how I change the cache configuration, as long as there's not enough capacity, it's going to be a miss anyway. That's capacity miss. And the third type of miss is conflict miss. So conflict miss means that, okay, I remember it. But when it's a midterm, I just don't know how to write it down, right? That's conflict miss. What does that mean is that, okay, it was in a memory before. It was in a cache before. However, for some reason, like for example, okay, I studied MDOS law. But later on, the professor teach me C equal to ABS, and then I forgot MDOS law, right? Because I only have one memory. I can only remember one formula in mind. So it turns out that the C equal to ABS kick out my MDOS law equation. That's conflict miss. Question?
Is a miss which we talked about last class is conflict mix?
That's actually a question we are going to ask you. So now, we talk about the 3 C's, and since you asked the question, let's answer this question. All right, let's see. Okay, so it looks like the initial vote, we have a little bit sparse answers. So why don't we discuss with your friends for another 90 seconds and let's sync up after that.
Yeah. And then for this one, they were like every time you wanted to access. So minus the first five, 25. Seems higher. I guess that was yeah. Which I guess was. But I mean, it's definitely not a wizard. Like big. I think you just need to like draw it out from each one. I think you need to use this formula to figure out. Yeah, yeah. And then we draw it out. Because after the first one, like, I gotta practice this question. It takes me a while. I think it's 100. It doesn't matter.
All right. So after discussion, okay, so we have 36% of you think it's D, 36% of you think it's E. So it's D or E. What's D? So D means 87.5. E means 100%. So how many of them? So okay, so let's walk through it. Okay, since we have half and half. So for the first axis, what kind of miss? What kind of miss? What kind of miss? Compulsory miss. Why is it compulsory miss? Because it's the first time access, right? Okay. How about this one, B0? It's still compulsory miss, right? Because we never touched the same block again before, right? We haven't touched the same block again. How about this one? What kind of miss? Also compulsory, right? Because we never visit this block. How about this one? What kind of miss? Compulsory miss, right? How about this one? It's still compulsory miss because this is, again, the first time I visit this block, right? I never visit this block before. So it's a compulsory miss. Now, looking at this one. What kind of miss? Conflict miss. Why is it not capacity miss? So here's the thing. You got it. If you look at the whole cache, right? We have 32 gigabytes. How many space have we used? We just used 5 blocks, right? That's just like a few hundred of bytes. So the whole cache still have like kilos bytes of data, right? So there is capacity. But because the structure, we map these blocks to the same set. So they are competing with this limited space. Within a set, there are still places that the block can go if your cache is not structured in this way, right? So this is actually a conflict miss, right? And why is it not a compulsory miss? Because the same block, right? It was there before. It was there before. It was there before, right? It got kicked out. It was there before. So that's why it's a conflict miss, but not compulsory miss. It's conflict miss, but not capacity miss. How about this one? What type of miss? Also conflict. How about this one? Conflict. How about this one? Conflict. How about this one? Okay. So if you keep going on, it's 100% miss rate. However, how many of them are conflict misses? 7 out of 8, right? So that's why the percentage of conflict misses is actually 87.5. So now, let's do the same on Intel processor and tell me, what do you think? All right, so let's take a look. Okay, so it's very interesting. So I still get 44% of you think it's A, C for, well, it's a very diverse answer. So why don't you go ahead and discuss with your friend for another 90 seconds and maybe we can figure something out.
Just compulsory is just like what it had it has more. So the first one, then I'm that's like I think because I was saying for the they each get to because they have because yeah, that's what I'm saying. So A, B, C, D, and E.
All right, let's see what you guys have. So after discussion, more of you think A. Why is it A? Why is it A? So what is this question asking about? What is this question asking about? How many caches misses are compulsory misses? Is there any problem in this sentence? Is the sentence clear? Okay, so sometimes I feel when people are complaining about I'm confused on Piazza, and I check my sentence again and again, I don't feel like there is anything should be confused. Because I do have sentence like this a lot. It's more about, did you pay attention to it? So what the question is asking about? How many of the misses are compulsory misses? How many of the misses are compulsory misses? So after reading this sentence again, can you tell me how many of misses is compulsory miss? How many of misses is compulsory miss? All of them. All of them, right? So if you go back and look at that, compulsory miss, compulsory miss, compulsory miss, compulsory miss, you all agree, right? It's a hit, right? It's all hit. Still a hit. Still a hit. Still a hit. Still a hit. What type of miss is this? It's a compulsory miss again. So the only type of miss you will see in this pieces of code, when you run this on an Intel processor, there's nothing else but compulsory miss. Agree? So if there's nothing else but compulsory miss, how come it couldn't be 100%? Right? So 100% of the misses here, they are compulsory miss. So sometimes you are thinking about the majority is right. A lot of people during the midterm, I don't see their eyeballs focusing on their own midterm, but others. And turns out, because I typically would have like tens of multiple choice questions in the midterm, and turns out midterm is the multiple choice questions are the ones that almost no one get 100% credit. Well, part of the reason is because you don't trust yourself, you trust others. Right? But the thing is that sometimes majority is not going to be right. You need to use your own judgment, right? So for this question, if you read the sentences carefully, 100% of them are are compulsory misses. All right. Are we all good about these three types of misses? Okay, question?
I'm just a little confused. Why would they be compulsory and not like capacity misses?
Okay. What does that mean by capacity misses?
Like there's not enough space to accommodate the.
There's not enough space, right? So how many? So when we have this misses, how many blocks have we occupied in a cache? When I have this miss, how many blocks have I occupied in a cache?
Is it not 8?
How big is the cache?
Oh, I see.
Right? So this cache has 48 kilobytes. And so far, what I use is only
the
5 of them.
I see.
Right? That's not capacity miss. All right. So let's talking about how can I change the hardware configuration to improve misses. So check this question and tell me what you think. All right. So the first round of voting, I have C as the most popular answer, but it is also D for 30% of you. So why don't we sync up together and discuss with your friend for another 90 seconds. What's your name?
Oh, on?
This one?
No, the fourth one.
Okay, can you press it?
Okay.
I guess like the amount of time to get the data from the cache.
Your name, please.
Sorry?
What's your name?
Oh, Abdullah Chaudhry.
This one?
Yeah.
All right. I will tell you later. Can you guys find your name here? Okay. How about you? Okay. Can you find your name here? How about you? Can you find your name here?
That one is yours. Yeah,
Okay. Can you put your name here?
I don't see my name. But I was the one that had the issue with the grayscale. But then I fixed it.
Oh, really?
Chandran is my last name.
What's your first name?
Rohit? Oh, did I look at it the wrong way? Oops.
Yeah.
Oh, I'm sorry.
Can you find your name? This is my first name. Oh, sorry. Find your name, please. Your names. Your name. Okay. Your name. Let's just click it. Your name. Your name. Okay. All right. Okay, let's see. Okay, after discussion, the answer is concentrated at C and D. So now 50% of you in C, D for 46%. So most of you think it's either 2 or 3. Okay, so we just do a sign up sheet. And the reason why I'm doing it is because, like we have the peer instruction, and I see there are 21 here, but there are apparently way more than that in a vote. So I just want to figure out who are the else, and I think that's Do you guys all agree that's some kind of cheating? Right? So we would definitely like to hear the explanation from them. And also, okay, the reason why I want to do that is because it's very annoying, right? So sometimes I see the answer is really diverse. And then I try to give you another 90 seconds to explain with others. But turns out that maybe everyone here understands, right? It's just other noise because like we don't live broadcast this class. So maybe they just watching it somewhere else and randomly press some answer. That's actually disturbing the classroom teaching. So that's not tolerable. Okay, so and that's why I want to do the sign up sheet. I mean, it's okay. And as I mentioned, and sometimes I feel bad about doing this because people here, you are here because you know. But for people who didn't hear this, they don't know, right? So the problem is that it's okay that you are not here. And that's why I'm giving like 50% grace for not coming here, not answering those questions, right? 50% is a very low threshold already, right? It's like, okay, you only need to come to 5 weeks of class and I give you 4 credits for the attendance and still want to cheat on that, right? I don't understand why. All right, so first, increasing associativity can reduce conflict misses. Do you guys all agree with that? How do you know? You what? You saw? The last good question already show you that, right? Like that's all what we were talking about, right? So see, the Intel Core i7 has no conflict misses. Why? Because it has 12 ways, right? So increasing way associativity does reduce the conflict miss. How about the hit time? So there is no free lunch. There's no free lunch. So some people might be asking, if increasing way associativity is such a good thing, why don't I just build many ways of cache so that I would have lower miss rate? And the answer is that you can't. And why you can't is because the hit time is going to increase. So the hit time means the normal access time if it's a hit, right? So the cost of increasing way associativity is that the red map, right? For the red map, it's just a hash. Directly access the block. If it's there, then I got it. So that's the shortest latency for accessing the cache. However, if you increase the way associativity, then every time you access the cache, you need to activate multiple blocks within a set. At the same time, not just that, you have to compare many of them. And all sorts that what I'm talking about here, they can all be done in parallel. So far it's good. But now, one last stage, right? You have to figure out if there is a hit or miss. And that's the only thing we cannot parallelize. You need multiple muxes, multiplexers, to figure out if there is a hit or miss and who is the hit or miss, right? So that actually delays the latency of accesses. So what does that mean? What does that mean is if you don't have good process technology, you cannot actually manage the hit time within a manageable latency, right? So a lot of people would say, hey, why ARM processor doesn't do multiple ways in their cache design? And the answer is that the foundry company cannot really manufacture the memory hierarchy they want. So that's why foundry matters, right? Like, although a lot of people would think, well, TSMC. I mean, I'm from Taiwan, so I should be proud of TSMC. But the thing is, some people think TSMC has the best fab all over the world. But I'm also an Intel alumni, so I know the difference between their technologies. And to be honest, the memory part, I mean, Intel used to be a memory company back to almost like 30 years ago. So they have the roots as a memory company in the past. And the truth is that their foundry are optimized for everything that is necessary for producing microprocessors, including the memory hierarchy. So TSMC, they did a good job in putting everything together, but they cannot manage the production of memory hierarchy in a way that we want the short latency for multi-way. So that's why all the ARM processors, they are kind of like suffer from the memory hierarchy. Because to be honest, later on, after the midterm, you will learn all microprocessors nowadays, the ways how they execute instructions are not too different. What really makes the huge difference is the design of memory hierarchy. And Intel's memory hierarchy, in fact, is probably the best. So that's why, and one evidence is here, is that except for Intel, no one else can have so many ways associativities in their L1 cache. So that's a proof their process technology is indeed practically better. Okay, and the reason why it's not easy to build multiple caches is because it will increase the hit time. And also, increase the block size, right? You need to fetch more data, right? You need to fetch more data during each miss. So it will increase the penalty. It will increase the penalty. The penalty means every time when there is a miss, how much time I need to service this miss. And increase the block size means that every time when there is a miss, I have to fetch more blocks. Increase the block size can reduce the compulsory miss. Do you guys all agree with that? Why not, right? Compulsory means the first time miss, right? So if you fetch more blocks, if you fetch a larger block every time you have a miss, then the chances that you have to fetch a new block or the elements each block can contain is actually more. So the amount of compulsory misses would be reduced. Right? Okay, let me give you another real life example. Right? Before every lecture, we have something called reading quizzes. Right? And the more you read, the less become something unknown during the lecture. Do you agree with that? If you read a book in the right way, right? So you can consider like compulsory misses is like the reading quiz that you prepare, right? The more you prepare, the less likely you are going to miss something. All right, so turns out, 3 of them are correct. The only one that is not correct is that increasing the L-way associativity does hurt the hit time, the access time. Okay, so now, let's back to this. So a lot of you would think, if I'm not Intel, does that mean I cannot produce a processor with very efficient memory hierarchy? Is there any remedy of that? Right, like this NVIDIA Tegra processor, right? It's still on sale very well, right? But for this kind of code that you probably write every day, it does have like this high miss rate, right? You don't want a processor like that. But, well, or on the other hand, you cannot prevent programmers to write this kind of code unless they take computer architecture before, right? Is there, and sometimes I feel like hardware designer, they are very thoughtful in a way that we try to make everything transparent. So we allow the software programmer to write crummy code and we make it work. So this paper by Noam Jopi, he's going to tell you how can we accommodate the situation where my cache has very limited associativity. And that should be a paper you have already read, right? So to test by how much you understand, can you tell me from what you have learned from this paper, based on your understanding about the cache behavior of NVIDIA Tegra X1, how many of the following techniques that this paper mentioned would work as a remedy for the situation that we are facing? All right. Okay, this time I got the exact number I want for the classroom. Interesting. All right. Somebody must have the way to know what's happening in a classroom. All right. So let's see what's the initial vote. So the initial vote said most of you think the answer is C, 45% of you, and for D it's 27%, and for E it's 18%. So apparently no answer is surpassing the threshold of 50%. So why don't you guys talk to each other and remind yourself what the paper is talking about in each and why does it work or why it doesn't work. All right, so let's see. What do you guys have after discussion? Okay, after discussion, the distribution remain the same. C, D, E both have their own advocates. So, and how many of you indeed remember the context of the paper? Not a lot. What do you guys have in mind? Is this the one? Oh, not this one. Sorry. For this one, right? What is miscaching? Does it help? What do you guys think? Does it help? What?
I cannot remember the difference between miscache and victim cache.
Okay, but you cannot tell the difference between miscache and victim cache. But do they help?
I think they help.
Both of them will help. Okay, 2 of them. How about string buffer, prefetch?
Yes.
Yes,
For sure. Yes.
for sure.
I'm pretty sure.
You are pretty sure? Okay. Okay. Let's take a look. Okay. So let's start with prefetching. All right. So prefetching, what does that mean by prefetching? From the word verbally.
It's like when you preemptively get more blocks than you need when you go to retrieve something, I believe.
Okay.
And you keep it in its own cache.
That's a very good explanation, right? So prefetch is like, okay, in addition to the block that is currently requested, I can foresee, okay, if you need this block, it may be likely you need some others, right? So that's called prefetching. So how does that work? So let's take a look at this pieces of code. It's a very, very, I would say, common type of code that you will write when you want to initialize an array with random data, right? Agree with that? So what typically will happen during cache, this pieces of code is that, okay, first of all, when I enter this loop, I start with D0. Is this going to be a hit or miss? It's a miss, right? Because if this is initialization, as I mentioned, this is probably the very first time I touch this pieces of code, right? So it will be a miss. So to service this miss, what do I need to do?
You have to go to L2 and then
I have to go to well, yeah, I will have to go to L2, right, to fetch it, right? Okay, so then it would take a while, right? So that I would get the whole block back and place it in a cache, right? So when I access D1, is it going to be a hit or miss? It's a hit, right? So finally, after I resume the execution, the next one I'm visiting is D1, and it's actually a hit, right? Until I access D8, if the block can accommodate 8 elements. Hit or miss? It's going to be a miss again, right? That's a common pattern of memory accesses. Okay. So what if I do this? So every time when I have a miss, in addition to the one that I'm requesting, I also fetch the next one. Because based on the behavior of the code, it's very likely that would happen. Agree? Right? So what I can do is when I find there is a miss in D0, either through software or through hardware, I issue a request called prefetch. And why is it prefetch? Because this is something I predict to happen rather than the actual request from the software. So it will be given lower priority in cache misses. So what in handling cache misses, right? So what will happen is that because it's a prefetch, so it was given lower priority. So I still have to access the first block that I requested from the L2 and return it to L1 and then the processor. However, what's happened here is that after this cache message is serviced, then I can service this block that the prefetch requires. Then, in the meantime, on the processor side, I continuously access my D1 through D8, D7. And in parallel, the L2 can find the block with D8 to D15 and then return it in the background to the L1. And then the next time when I access D8, it will be a hit. Right? And at some point, you can continue prefetch others. Right? So that's the idea of prefetching. So prefetching is the idea that either through software or hardware, you try to identify or you can guess the access pattern and then fetch data instruction before the application asks for it. Right? That's prefetch. So there are two types of prefetch. One is hardware prefetcher. And another reason why Intel processors are potentially more performing than others is because they have a very smart prefetcher. And the prefetcher, the hardware prefetcher, they keep observing the memory access patterns and then try to find some regularity within that pattern and then predict what's going to happen. Right? So, you know, I feel very interesting. So a lot of people would think we are computer architects. We have nothing to do with machine learning. But don't you feel like even in microarchitecture design, there are many machine learning problems like this? How can you predict the future memory access? Right? And that's actually one of the big topics that computer architects has been addressed in 20 years ago. So, and very interesting is that recently, if you attend any computer architecture conferences, you will figure out that people are doing a lot of machine learning research regarding how to accelerate machine learning. And I feel like computer architecture community becomes a machine learning community in somewhere. And some of our colleagues, they do, although they are computer architects, but they do publish in big machine learning conferences. Because of what? We learn a lot of machine learning when we study computer architectures, right? So this is one of the example. And another distinction between us and conventional machine learning folks is because we are computer architects, so we are more realistic. We are focusing on the stuff that can be done, right? So that's why sometimes our work is more welcoming, right? So this is the idea of prefetching. So hardware prefetching, we use a hardware prefetcher, and you can consider the hardware prefetcher, they have some heuristics to learn the access pattern from the program, and then prefetch data. Another way to do it is called software prefetch, because no one, presumably, no one knows better about the behavior of your code than you. So the software prefetcher means that the software programmer, they can issue some kind of prefetching command or prefetch instruction for their code. So here I'm going to give you a demo. So x86, they provide an instruction called mmprefetch. And you can also use GCC flag, use compiler to insert prefetch flags. And let's see how the prefetch works for the performance. I'm not sure this demo will work though. So wait, is this the right one? Okay, let me figure that out. Yeah, I don't think I got the right one. I think. So this is the demo we have the last time. Okay, I don't think I got the right demo. Okay, I owe you a demo next time. But you know what? I still want a demo. Okay. Let me figure out if I have the demo somewhere. Is it? Is it this one? Okay. Here we go. Okay, let's try another demo. The demo. Oops. Okay, so here I'm going to talk about prefetch. So I guess the reason why I typically don't have wait, where's that? This is incredibly long. All right. Prefetch. Okay, x86 provide prefetch instructions. As a programmer, right, you can actually use prefetch. So here I have some code called matrix transpose. And like, okay, so here I want to explain a little bit because this is a highly optimized code that tried to use vectorized way of dealing with matrix transpose. And here, what I'm doing is that I try to enable a prefetch here to prefetch the next row when I want to do the prefetch, when I want to perform it. So let's take a look of what's happening. So this is an Intel processor. So with software prefetch, this is with prefetch, right? Without prefetch instruction, it takes 0.57 seconds. And now let me turn on the prefetch. It does help a little bit, right? As you can tell, it improves the performance slightly, right? So that's the usage of prefetch through the instruction. So now, take a look at these 4 pieces of code. How many of the following can prefetching effectively helping improving the performance? All right, let's take a look. So the discussion show, well, without discussion, BCD have around 30% on each of them. So why don't you guys discuss with others regarding how many of the following that prefetch can help? Which one? What? Yeah, that's a like a for loop thing. All right, so let's take a look. So after discussion, so most of you think the answer is C, 61%. So two of them could get benefit from prefetching. So how many of you agree with you that prefetching can help on the case of number one? Okay, you look around and figure out. No one raised their hands. So why cannot? Why prefetching cannot help this one? What? Why we cannot help on linked list? Okay, here's the thing. The next pointer, without really fetching the content of the next, you cannot accurately predict where the next place is, right? So a lot of people, they like to use linked list, but it's actually a disaster in terms of performance. And I think I do have a demo. Let me see. Do I really have the demo here? Okay, better data structure. So that's the array of objects. Okay, probably not this one. Okay, let me show you the demo next time. But I do have a demo. Tell you how bad linked list is. Okay, so linked list, as I mentioned, right? Because the next pointer is hard to predict. So the prefetcher cannot help. Software prefetch cannot help either. So how about the second one? Why? It's random. Okay, so here's the thing. Although there's a random in there, right? But what's random is actually the value, not the memory access, right? So the second one, yes, we can help, right? How about the third one? You think so? Why?
I believe you can store a binary tree adjacent in memory.
You can store a binary tree adjacent in memory, but how do I know if I'm going to the left or right? And what if they are in different blocks?
You don't, but there are, like, you might access only left or only right for some applications.
Yeah, but that's still hard to guess.
It is, but I figure the hardware prefetcher might be able to.
Okay, so I would say it's still hard to predict in general, right? And the case that Ben said, there may exist, but may not be happening so often. And in fact, Ben, you are saying about a case where it's not very balanced. But most of the time, when we try to organize the data structure, unfortunately, we try to keep the access as balanced, as random as possible, right? So it turns out, because our software programmers are so caring about the complexity issue, so it turns out it's not optimized for memory access patterns. So in a general case, it's actually going to be more randomized, so make it hard to predict. How about the fourth one? You think it's yes? How do I know the next? How do I know the next? I don't know the next, to be honest, right? Can you tell me what's the next? It's actually difficult to know, right? So it turns out only two of them, or only one of them could be perfectly addressed by prefetching. So, it's very important as a software programmer. You need to write a code that is easy to predict. Although there are hardware optimization like prefetcher, however, if you don't write your code in a good way that makes it easy to predict, your performance is not going to win anyway, right? Okay, so let's continue talking about prefetch. So is prefetch a good way? So the thing is, okay, the question is like, okay, after I prefetch is basically fetching a block. And I have to place it somewhere. If I have a direct map cache, what would happen? It will have to be mapped to one position in the cache to store that prefetch block. But if I have direct map cache, what's the likely consequence? I will kick out somebody. And because this is a prefetch, it may or may not happen. So actually, you are letting something that you predict to kick out something that's already in a cache. Is that a good thing? Is that a good thing? So that's the problem of prefetching, right? So let's look at this Tegra X1 with prefetching. So now I have this, right? So far, what I'm going to do is that, okay, I always do the next line prefetching. So as you can see, when I access A0, I always try to access A8 to A15, right? So now, when I have E, miss, I also prefetch E8 to E15. How about the others? When I try to accommodate this E8 to E15, what would happen? Others are kicked out, right? So what happened is that although you do prefetch A1 and A15 before, but because E8 to E15, when you prefetch it, it will also kick out others. Nothing changed. Nothing changed. Still 100% miss rate. So does prefetch work? Not at all. So another idea that Nong will be talking about is string buffer. So the reason why prefetch doesn't work in this particular case is because when you prefetch data, it still needs to occupy your cache. And if your source is originally conflict miss, naively adding prefetch is actually going to intensify that conflict miss, because you are potentially kicking out the data that you need. So a remedy of this is that we just don't let those prefetch blocks occupy the original cache. And that new place is called stream buffer. So the idea of stream buffer is very simple. Instead of putting the prefetch block into the cache, the original cache, I add a small buffer called stream buffer to store the block that I prefetch. So only when I cannot find the block in the L1, I will consult the stream buffer to see if I have the block. So if I have a miss, and I will consult the stream buffer to see I have it in a stream buffer. If it's luckily in a stream buffer, then instead of going to L2, I can directly get the stuff from stream buffer. That's stream buffer. So prefetching itself doesn't help Tegra X1, but with stream buffer, it would help because at least I can reduce the compulsory miss. Now, miscaching. That's something that Ben get confused with victim cache, right? So let's take a look at what is miscache. So miscache is a small cache that captures the missing blocks. So what does that mean? Is when I load a data or store a data, if it's a miss, when I get a block, in addition to return it to the L1, I also give a copy to miscache. I also give it a copy. So what will happen is that, okay, if unfortunately this particular block, that B, get kicked out because of a conflict miss, I still have one copy in a miscache so that I can reduce the conflict miss. So Ben, do you think it's a clear enough this explanation of miscaching?
Yeah.
Okay. But as you can tell, there's one problem here. Every time when I miss, I will actually create duplicated number of blocks. One in L1 cache, the other in miscache. And you know, every memory cell costs. So another idea of improving miscache is called victim cache. So victim cache is called victim cache because unlike the miscache, it gets a block every time when there is a miss. It only have a block when the block get evicted from the L1 cache. So the way how a block entering the cache, the victim cache, is different from miscache in a way that for miscache, a block enters the miscache when there is a miss triggered. And the missing block would have another copy in the miscache. However, for victim cache, it only stores the victim block when a cache miss happens. So in your cache, you would have a storage for the requesting block. In the victim cache, you are going to have the block that was a victim because of the priori victim cache miss. So for the problem with Tegra X1, what you can imagine is that whenever I get E, whenever I get the original A kicked out from the cache, this A will be stored in the victim cache temporarily. So when I access A, although it's still not in the L1, but I can find it in the victim cache. And for miscache, it's more about, I have the A whenever the A was a miss. So I can also find it there. However, the space efficiency, as you can imagine, is worse in a miscache because you will have two identical blocks, one in the L1, the other in a miscache. However, with victim cache, we only store the ones that are kicked out from the L1. So effectively, there is no duplicated copy. Is that clear? And as you can tell, both of them would address the issue of conflict misses. So if we look back to this question, prefetching itself doesn't help. However, prefetching plus stream buffer will help reducing the compulsory misses. And victim cache, miscache, they would help. However, comparing against victim cache, missing cache has higher hardware overhead because of the duplication of the block. So that's the summary of the hardware techniques that we learned from GNOME Drupi. And in the next lecture, we will continue talking about some of other remaining hardware optimization, we are going to talk about the software optimization. But before you leave the classroom, don't forget we have reading quiz due next Tuesday, and assignment 3 is already released, and we have office hour today at 2. And also, a lot of people, I read your comments about this class, and most of the comments fall into AutoGrader. And I want to mention, don't be lazy, first of all. Try to make your answer as clear as possible. Sometimes it's, I don't accept an answer that only have the result, but not the progress. And it's not about the AutoGrader. I will do the same in your midterm. So try to make it as detailed as possible. If you feel like there's a place you should use LaTeX syntax, use it. And also, this is a class that we like you to learn from your experiments, learn from real practice. So there is no point you should get a number from somewhere else but your measurements. So if you have a measurement that's already included, you should actually use the measurement you got as an answer instead of, and this is just copy paste, right? So it's not about formatting. It's not about AutoGrader is trying to like trick you. It's more about, okay, why don't you, okay, a few things. Don't be lazy on answering your, presenting your answers, but sometimes if you can copy paste, just copy paste. All right? Other than that, enjoy the rest of your week. I will see you next Tuesday.